Well, the very first thing that you should always consider when you are trying to compare between models is domain knowledge. There is nothing better than domain knowledge when you try to analyze data. Now, domain knowledge may take a number of different forms. The first thing is whether there is any theoretical justification behind the model that you are using. We have already seen one example of this. For example, when we worked with those gravitational things, that is project 1, and we saw that the quadratic fit was possibly less good than a cubic polynomial fit, but that quadratic fit was dictated by the underlying physics model. So merely switching from the quadratic to cubic on the fly is not a good idea. So you should think about the domain-specific theoretical justification. Then, in most cases, whenever you have a domain, there is a reason why you are analyzing the data set. So there is the question of what is the actual loss that is incurred if you go for this model as opposed to if you go for that model. So just try that. Of course, this may be very expensive. It is just like trying to figure out whether something is a poison or not by actually swallowing it. But still, this remains the best possible way. Now, of course, you can have a kind of proxy to that, which is the cross-validated version of the loss. And for that, what you do is you have your data set, you cut it into two parts, typically a smaller part and a larger part. You take the larger part and fit that in your procedure and reserve the smaller part as your test data. That is going to be the proxy for your future data. So try to see how your model fit based on the larger part performs on this smaller part. So that is the idea of cross-validation. So these are techniques that involves the domain, and these are by far the best techniques to use if you can afford to use them. While domain-based methods remain the best ways, in many cases you do not have any such hints coming from the domain. So then you have the different models and you have your data set. So somehow you have to decide based on only the candidate models and your data set which one is the best fit. In that case, a very useful way of proceeding is to think in two steps. First of all, how good is the fit? And secondly, what is the price that you have to pay to achieve that good fit? Now, there are various ways by which you can balance this trade-off. The most popular way is when both your models are fit using maximum likelihood estimation. There are lots of different ways by which you can fit a model. You can have just plain ad hoc things, or you can have things that are just mathematically motivated things, just like least squares, without having any kind of underlying probabilistic assumption. But the discussion that we are going to do revolves around the setup where all the models are fitted using maximum likelihood estimation. In that case, how good is the fit? That may be conveniently measured by the maximum value of the log likelihood that you have attained. Similarly, the price that you are paying to achieve that fit, that may be conveniently measured by the number of free parameters that you had to estimate in that model. So that is the trade-off. If this goes up, you are happy. If this goes up, you are unhappy. So how do you balance them?